So our next speaker is Ronald Coifman from Yale University.
Well, I'd like to actually continue the prior talk, which is point to another elephant in the room, which is that we really don't have a good description or a good language to tell us what the net is doing and what it's extracting. I mean, we have seen examples on ImageNet, for example, where you sort of can relate various hidden units to some features in an image. What we really would like to do is actually go much further and, in fact, find out what are the internal latent variables which describe the data and which allow us to go to the next step. I mean, we are basically in a sort of Tower of Babel type situation. We may have hundreds of deep nets and we don't know how to compare their outputs or how to compare their internals as they are. So how do I change slides here? No. Oh, yeah. Okay, got it. That's fine. So the point is, the challenge is really, so at this point I would say on some level, when you use a deep net for regression or an autoencoder and so on, you're basically tabulating, building various codes to describe data, and then use those codes to reach your goal. What I'd like to suggest is that it would be very useful to find an intrinsic language which describes the internals of the net, the features that, for example, in ImageNet you had, which are human features, or the features that you get when you actually do language, and so on. But you want the net to actually basically extract those features from the data. So let me give you an example. I think the example is really going to be quite illustrative here. So here, there is this molecule, the alanine dipeptide, which vibrates in water. And we have two observation systems. You can think of them as two neural nets if you wish, but you have two observation systems. I'll return to neural net in a minute. And on the one, you observe, say, the colored atoms, and you look at their vibration. So you have cameras that observe them. You look at their vibration in the water. On the other side, you look at the other atoms, and you look at their vibration in the water. And you want to know what is the underlying latent variable that allows you to characterize the shape of the molecule at any given time. So what happens in this case, we are sort of building a Siamese network or a network that allows us to intrinsically find latent variables for the observation of the colored atoms. And those two latent variables are the two axes that you see on the screen here. So you have this and that. They correspond to the observation of the colored atoms. Here you have those correspond to the observation of the other atoms. And you see the variable looks the same. The color that is painted here is exactly the angle that you have here. So in this case, we actually know the truth, and the truth helps. And you know that the shape of this thing is governed by those two hinges. But we derived this two-dimensional parametrization directly, intrinsically from the data. We could have trained a deep net that would have extracted those two parameters. Here we just did it based on matching the statistics. So basically, what is the main theme an idea lying behind it, is that at every point in time, we sort of observe a cloud of positions of that molecule, and the statistics of the vibration of that cloud and the changes of that statistic, not the statistic itself, but the change of that statistic is intrinsic to the underlying dynamics floating underneath it. So we measure the changes of that statistics, or effect, as a way of comparing, say, two states of the molecule to each other by comparing basically measuring the probabilities that state X and state Y are the same. Essentially, that's our input. Here we also can measure that probability that two states are the same by comparing statistics. And what happens is that we have generated essentially a probabilistic kernel that compares one state to another by saying X is equal, the probability that X is in the same state as Y, the molecule is in the same shape, is known to some precision. So here you have two systems to measure that thing. Their probabilities are, you can validate that they are actually quite consistent with each other. And so you know by definition that the eigenvectors of this kernel, if you wish, which is a probabilistic kernel, are independent of anything. They don't care if I measure those observation or those observation here. It doesn't matter. I'm measuring a probability that two states are identical. And so the point I want to say is that this ability to measure match of probabilities is something that is done actually quite frequently within the context of neural net. For example, you can build Siamese nets in which you have two sets of data, you have two pieces of data, X and Y, and you basically want to encode X and code Y that can come from different sources in such a way that the correlation between the codes will correspond to the probability that the two states are related to each other. This is sort of the generalized version of canonical. So when you do SVD on that, it's a generalization of canonical correlation analysis, which has been a mainstay of a lot of statistical matching. So I'm saying there is a way of actually getting parameters from the data which are independent of the way that we actually observe the data. Now that's remarkable because generally speaking, it's not being done, not within mathematics, not within any other place, except maybe in statistics you have basically principal components, but that's about it. And they should be, but here the parameters that we get are really quite independent. So basically it comes to, I'm summarizing it again, given a set of observation, we can encapsulate the knowledge by building an affinity kernel, which is just a generalized conditional correlation, so the probabilities at 2 points are the same. Or you can build a Siamese kernel, and again, the Siamese kernel will measure the probabilities that two measurements were done at the same time, for example. Now that's particularly useful if you have observation measured simultaneously for many sensors and they have to be consistent. Now the point about that is that the SVD of such a kernel is intrinsic. It's just related to the probability. It doesn't relate to the measurement. So the issue is how accurate was your probability. So coming back to the questions we heard just before I came on, which is issues of instabilities and so on, this is a way of, say, you have two architectures which basically can build two autoencoders of the same set of data with different architectures, with different initialization, if you wish. And you can ask to what extent are they consistent with each other and to what extent are they reasonable. And so the answer to an answer to that would be use your autoencoder to estimate the probabilities that 2 points are really essentially indistinguishable to a given level of precision. And if they give you the same kernel, essentially, then they're interchangeable and they have a common language. And the common language are the eigenvectors of that kernel, because they do not depend on how you measured it. By the way, a situation in geometries that this has happened but not recognized is you take a Riemannian manifold embedded in high-dimensional Euclidean space isometrically, and then it's embedded again in some other high-dimensional Euclidean space. You have an atlas for one, an atlas for the other. You have a change of variables from one to the other and all of that. It's completely idiotic because when you have this Riemannian manifold, you know the neighborhood of radius epsilon around every point. You also have an operator which is the averaging around every point on that ball. And you can do it in both settings, and the eigenvectors are the same. So they are the eigenvectors at Laplacian. And it's quite known, it's a real theorem, that you can select around any point a set of eigenvectors that gives you a coordinate system which is as broad as possible in the neighborhood of that point. So this is a mathematical version of what I'm saying here. So this ball of radius epsilon, the probabilities that 2 points are within epsilon of each other, if you wish, or are equivalent to that precision. So what I'm saying, there is a way of imposing a common latent variable, as I would call them, on systems like that. So let me continue here. Again, let me take this. So we were actually doing an experiment in neurology, but before that we are doing an experiment in mechanics. So you have this pair of penduli which are oscillating at the spring constant between them is changing over time. So the rate of oscillation is increasing substantially. It's vibrating like this. There's oscillation of this kind, and then there's oscillation also where the spring is not affecting the distance. And those are the sort of nonlinear normal modes exist in there. Now, suppose what you have is you take this data, you take a video camera, you image it, and then you do a random projection of that image into 100 dimension. You get this flickering movie here of the vibration of the pendulum, which we viewed as a sort of model of flickering in brain imaging, with calcium brain imaging. We had some images like this for a mouse. I'll show you in a minute. And the issue is, can you actually, in this case, derive from those fluctuations, just it's the only thing that you have. You want to derive the actual latent variable that describes the whole data. And the latent variable is, here it is. So the yellow one is basically essentially related to the spring constant, and the red one relates to the normal mode corresponding to the flat, to the non-extension of the spring. By the way, we are outside the linear regime here in this pendulum, plus the constant changes. So that was the point of doing that. The real thing that we were doing, we were looking at calcium imaging of the brain of a mouse while he was performing a repetitive task of grabbing for food, as is seen here in the images. And what you see, what the images you get look like that. I cannot run the video here, unfortunately, but basically the measurements you get are sort of fluctuation. The white spots there are fluctuating like the spots I had for the pendulum before. And out of that, what you do is you build a different, so for every pixel, if you wish, in this thing, you have a profile of fluctuation over time. That's your data, and then you want to organize the latent variable of those profiles. In this case, if you just look at the pixels as your rudimentary object, the latent variables of the profile are just the neurons themselves, which you see on the right. And so using many experiments, you get the geography of the underlying neural structure, and the sort of pink or purple thing is basically the activity of the different regions. I mean, we did that as stage 0 to do the real thing, which is to compare the profile of activity at different times, different experiments, and try to match them. We were surprised to find, which I'm sure every neurologist will tell you that that's the case, that he can do the same thing, but the thunderstorm that we see on the green image is different every time. So So the point was, how do you actually derive now from that the underlying latent variables that drive the dynamics of the system? So our program has been, well, we do it for physics. If we are happy with what we get as latent variables of the physics, then we have some hopes that we'll succeed in doing something useful in this range. So the main issues, there are lots of mathematical issues which are sort of always hidden. How do you compare situations which are quite different from each other but really equivalent, and how do you define metrics of that kind of equivalence? You can use things like transportation metrics, earth mover metrics, and they would do a good job. The other issue is, if you have a lot of data, finding eigenvectors is a monster problem, but say I have a million by million or a billion by billion matrix, I cannot do that. On the other hand, you can train a neural net to actually give you the projection on the first 10 eigenvectors of this probability kernel that you have. And this is a project we are working on now. And it's quite useful. So the neural net allows you to sort of scale up the system substantially. With that, this is just opening a challenge, I would say.